Okay, so now we're going to take a look the last section here, how we can calculate the delta H for different processes using the delta H's um, for other reactions. And what we're going to do is going to apply what we learned early on, which is Hess's law, to this calculation in a process known as the Born-Haber cycle. So the Born-Haber cycle is something that is going to relate uh, a concept that we talked about before, which is the lattice energy for a compound. And the lattice energy itself is something that is very difficult to measure. However, we know some of the other, and it's very easy to measure some of the other properties of that compound. And if we apply Hess's law to that process, we can actually calculate the lattice energy for an ionic compound by relating it to other quantities that themselves can actually be measured quite easily. So that process can be represented by a diagram that we call the Born-Haber cycle. And as the name suggests, it is going to be in a cyclical form. And it's represented in a very typical or very common way. So let's take a look at that process. We'll start off looking at a very simple compound. We've seen this before. So consider, let's say, sodium chloride, regular table salt, as a solid. And if we were to write the chemical equation that represents the delta H of formation for sodium chloride, it would be the formation of 1 mole of NaCl from its elements under standard conditions. So that would be sodium plus Cl2, chlorine gas. And in order to make 1 mole of the Cl, we actually have to have half of this. And whatever, we can look that up. Remember now, this is something that it's tabulated. So the delta H for this process is negative 411 kilojoules per mole. Okay, so this we've seen this before, the delta H of formation, standard entropy formation for compounds, the formation of 1 mole of that thing from its elements in their standard states. So if we consider that overall reaction, well, how does that actually happen in the first place? Well, this is where we're going to start now constructing a Born-Haber cycle. So we have here on the y-axis our increasing enthalpy, which again has a symbol H. So if we consider the formation of NaCl solid, okay, well, in order to make that, in order to produce that according to our reaction, that process is an exothermic process. So our starting material here, the sodium and the chlorine, actually have to be higher in energy than the NaCl. So we'll have our Na solid and our Cl2 gas that will be up here, higher enthalpy. So that process going from the reactant to the product will actually be going down, and that's our delta H here formation for NaCl. Right? So we're representing that process in a diagram, an enthalpy diagram to be more specific, enthalpy represented here on the y-axis. So we can get to this process, and again, the reason why this works is because enthalpy is a state function, right? So it doesn't matter the pathway. We can get from our starting material, our starting point here, we can get to the end product, the NaCl solid, going in one step, or we can actually go through maybe a whole host of other steps and end up at the same point. And we're going to take advantage of that as we go through this Born-Haber cycle. So in order to get to this, what we can also do is we can take that sodium solid and we can now convert it into sodium in the gas phase. And whatever the delta H for that reaction is, we'll call that step 1. Okay, and that process, the formation of sodium in the gas phase, if you look here on the left side, that is also in a table that we can look up. Okay, and then we're still going to have our half Cl2 in the gas phase as well. That delta H there is 107.7 kilojoules per mole. I'm just going to ignore the units for right now. We'll just work with the numbers. We'll insert the units here on the left side, so it applies to all of these values. The next thing we can do is we can take the half Cl2 and we can convert that into what we actually want, which is 1 Cl. So that process also is going to require energy. Okay, and that is another value we can look up in our table, and that corresponds to the bond enthalpy of chlorine gas. So here we're going to make now our Cl atomic Cl in the gas phase, and that process would require 121.7. So the delta H here for, we'll call this step 2. That's 127. kilojoules per mole. So now we still have our Na that we didn't mess with, plus our Cl in the gas phase. Now, in order to continue this, we're going to take our sodium and we're going to convert it into the ion, so Na plus in the gas phase, and then we're still going to have our Cl. And that process, that is the ionization of sodium in the gas phase. We'll call that delta H for step 3. All right, and then that process, according to our table here again, something we can look up, that is the first ionization energy of sodium, and that is equal to 495.9 kilojoules per mole. We'll continue this all the way across, and then what we can do is we also now need to get to the Cl minus, right? So going from the atomic chlorine in the gas phase, the chloride ion in the gas phase, that process is the electron affinity for chlorine, and that is also something that we can look up, right? So that corresponds to the chlorine gaining an electron to form Cl minus. We'll call that delta H for step 4, right? And that is equal to negative 349. Now remember, the arrows here are going to tell us what the signs are. So we're going down here, that's going to be negative 349 kilojoules per mole. So we have our Cl minus, and we still have our Na plus from the previous steps, our sodium ion, the gas phase, plus Cl minus. And then when we react these two together, Na plus in the gas phase, Cl minus in the gas phase, right, what we end up with is all the way back down to our NaCl solid. And that step, this last step here, oops, let me rewrite this. So we have our NaCl solid going from Na plus and Cl minus to the NaCl solid. That is the delta H, and that is the lattice energy. Of this sodium chloride that we're trying to find. All right, so if you remember the lattice energy, the formation of 1 mole from its ions in the gas phase, right, that corresponds to Na plus Cl minus to give NaCl solid. right? That's our lattice energy. And we can calculate that based on the fact that getting from this point to our NaCl is the same as going from our starting point going up all the way across and then back down to the NaCl in the solid. And that is the idea. That's the whole point of using this Born-Haber cycle and then incorporating Hess's law into this process. Remember, Hess's law applies the whole idea of state functions to that process as well. So what we can do now, right, is we can go ahead and make some equalities. So this step here in green, call it the delta H of formation for sodium chloride is simply the sum of all the other steps, right? So step 1, step 2, step 3, step 4, and the step of the lattice energy. All of that will equal this one step here because I can get to that point, right, going in this one step from the Na, the delta H of formation, or if I add together all the yellow arrows, right, I end up at the same endpoint. So I start at the same point, I end up at the same point. The numbers should be the same. So the delta H of formation is simply equal to the sum of all the other steps. So delta H for step 1 plus the delta H for step 2 plus the delta H for step 3 plus the delta H for step 4 plus the lattice energy. Okay, and we have these numbers. We can go ahead and plug these numbers in. All right, so I have my delta H of formation that I can look up. That is equal to negative 411 kilojoules per mole. Delta H for step 1 is 107.7. Plus the delta H for step 2, that's 127.7. Plus the delta H for step 3, 495.9. And then the delta H for step 4, now this is going in the opposite direction. Right, so that's going to be a negative value when we incorporate it. So the step 6 there is I'm sorry, step 4, not step 6, is the electron affinity. So that's a negative value, remember? So that's negative 349. And then we have our delta H here for the lattice energy. So when we substitute these values in, right, we move our numbers around, right, and we end up with our delta H here for the lattice energy being equal to, let's plug that into our calculator. Okay, so everything on the right side here ends up being this. So when we evaluate that, so we have 731 minus 349. Okay, that's going to give us, let's see, 731.3 minus 349. It's going to give us 382.3 plus the lattice energy. And that's equal to negative 411. So again, if I move everything around, so I move this over to the left side, negative 411 minus 382.3 would give me the delta H for the lattice energy. So that's going to give me something like 793.3. And then this is, let's make sure we keep our unit, 793.3, and that's kilojoules per mole. Okay, so remember now, this is a negative value because we're looking at the process going from the ions to the solid, and that process will release energy going in this direction. Alternatively, if you're going the other direction, you need to provide energy. That'll be a positive value. We'll need to provide energy to separate these ions from the solid into the gas phase, right? So remember, when we define lattice energy early on, right, depending on your point of view, how you approach it, it's either the energy released, when the solid forms from the ions in the gas phase, or it's the energy required to separate the ions in the solid into the gas phase. All right. So we can calculate that lattice energy by using this Born-Haber cycle that we just constructed over here. And the reason why it works is because we can use Hess's law and the whole idea of state functions to make everything, or to make this process here in green going in one step. Okay, so everything here, the delta H of formation, okay, going in one step is simply equal to the sum of all the other steps, but we can get to that same, starting at the same point, we can get to the same endpoint by going in a whole different direction, involving lots of other steps, and we can make those two pathways equivalent to each other, right? So the delta H of formation in one step, that's this here on the left side, being equal to the sum of all the other steps on the right side, and all we do is we solve for this one unknown, which is the lattice energy, right? That's not something here that we can measure very easily. We can calculate it, however, by taking advantage of Hess's law and the fact that delta H is a state function, right? So we're incorporating a couple of new things that we learned in this section to help us solve this particular problem of determining the lattice energy for our compounds, our ionic compounds. Now, remember, the lattice energy is an indication of several things, but it also tells you, it's an indication of how strongly those ions in the ionic compound are actually being attracted to each other. So the higher the lattice energy, the more stable that compound is, the stronger the attraction between the positive cations and the negative anions. So if you were to determine or calculate the lattice energy for a slightly different compound, so for example, if you have something like cesium chloride instead of sodium chloride going through the same process, right, we can use that Born-Haber cycle as a guide, and we can actually go through that process as well. So if I were to draw something similar as I did before, so I have my enthalpy here on the y-axis. So that's H. I can write out the solid here. So I have my cesium chloride, so CsCl in the solid. I can get to that from a couple different points, a couple different places. I can start off with cesium in the solid phase, reacting with half of the chlorine gas in the gas phase. So this would be here the delta H of formation of cesium chloride. And then to get back now from the starting point to the cesium chloride, I can go through the same set of steps all the way around and then back down into this endpoint, right? So the first step would be to convert the cesium solid into the cesium in the gas phase, and that would be the delta H of formation of cesium. We have our half Cl2 remaining. In the gas phase, right? So the change that's happening here would be going from the solid cesium to the cesium in the gas phase. The next step, we need to make the atomic chlorine, right? So we have diatomic chlorine here. So we can take now the Cl2, converting it into chlorine in the gas phase. So that's the next step that's occurring, next change that's occurring. And I still have the stuff remaining from the previous steps, cesium in the gas phase. Now we need to ionize that cesium. We can provide energy for that to happen to make the cesium ion. All right, so the change that's happening there is going from the gas to the ion. And I still have the other thing remaining from the previous step, all the way across. And then I need to then incorporate the electron affinity for the cesium. I'm sorry, for the chlorine in this case. So the chlorine is going to go from the Cl to the Cl minus in the gas phase. The change that's happening there would be yellow. So this becoming Cl minus, and I still have the cesium ion, the gas phase. And then the step that remains would then be the lattice energy as these two ions combine to produce the cesium chloride solid. That'll be a lattice energy. All right, so all of these other steps, we'll call this here step 1. We can look up that value in our tables. Step 2, we can look up that value in our table as well. Step 3 here, the ionization, first ionization energy for cesium, we can look that up. We have an electron affinity. The next step, we'll call that step. I'm losing track of my steps here. Step 1, step 2, step 3, and then step 4 would be the electron affinity. And then the last step would be our lattice energy. All right, so again here, the delta H of formation would simply be the sum of all the other steps. So step 1 plus step 2 plus step 3 plus step 4 plus the last step there, which would be the lattice energy, which is what we're trying to find. Okay, these are all static values. Put zeros in. All right, and then this is our unknown. We can solve for this. And all the others, we simply plug these values in. So it just becomes a math problem. Once we have our steps outlined, we're solving for the lattice energy for that particular ionic compound.